Okay. Hello, everyone. My name is Josephine Kerutt. I'm currently working at the University of Geneva, somewhere between finishing my PhD and postdoc. I'm working with Anne Ham and Pascal Oesch, and did my PhD in Potsdam with Lutz Wiesotzky. And I'm also part of the MUSE collaboration. So first of all, I want to thank the organizers for this very nice conference. I think it's a great idea to be able to share our science and discuss even in this difficult time. And also thank you for giving me the opportunity to talk here today. I will tell you about my project searching for Lyman Continuum emission and its connection to Lyman alpha emission using MUSE and the HDUV survey. So I guess for this audience, I don't have to advertise why Lyman Continuum emission is interesting, but just to give you a reminder. Of course, during the epoch of reionization, something has reionized the universe, and it's not quite clear yet what the contribution of galaxies to that is. Because unfortunately, Lyman Continuum can't be directly observed at the epoch of reionization, only if you have very clear sight lines in the IGM, because it is absorbed in the IGM, of course. And the goal is to find some indirect tracers, for example, through the Lyman alpha line, to estimate the Lyman Continuum emission through properties of the galaxies that can be observed up to very high redshifts. And several of these indirect tracers have been proposed in models already, for example, by Baham et al. But also some have been directly observed at lower redshifts, for example, in Isotoph, which you can see here. I think this has already been shown in this conference many times. So there is a connection between, for example, the Lyman Continuum escape fraction and the O3 to O2 ratio, but also between the Lyman Continuum escape fraction and the peak separation of the Lyman alpha doublet. So this is what I'm going to focus on. I want to find the connection between the Lyman alpha and the Lyman Continuum. So the goal of this project is also to look for individual Lyman Continuum Nika candidates and in the HDUV data to find a connection between Lyman alpha and Lyman Continuum by stacking objects. And also I want to highlight that it's important to make a good selection of the objects for stacking, to only use the most promising objects that can actually increase the signal. Because there has been a study already early this year by Bian et Fan who used the same data and also do stacking, but do not find a Lyman Continuum signal in their stack. So what is the data that I'm using? I already said I use MUSE and HDUV, and I use the MUSE data to find the Lyman alpha emitters. So as you know, MUSE is an integral field spectrograph at the VLT and has a field of view of 1 square arc minutes. And the redshift range, or the wavelength range of MUSE allows us to find Lyman alpha emission in a redshift range between 2.9 to 6.7. And I'm using here data from 2 surveys that were done with the GTO team of MUSE, which is MUSE Deep and MUSE Wide. And we use a blind search for Lyman alpha emission, so no HST priors. But this also means that we find lots of objects that do not have an HST counterpart because they are very faint and only bright in Lyman alpha. And here you can see the footprint of the data that I'm using of MUSE Deep and MUSE Wide. These are the little squares, and the shaded area is the HDUV survey, and they overlap nicely. So from the MUSE data, I get the information on the position of the Lyman alpha emitters, on their redshift, and also I get the spectral information, so the information on the properties of the Lyman alpha line, which will be important later on. And so with this information, I can start to look for a Lyman Continuum emission in the HDUV survey. And in this plot on the bottom here, you can see which bands I can use for this. So you have the redshift and the wavelength, and in the black line and the dashed line are the Lyman alpha position and the Lyman limit. So everything bluewards of the Lyman limit will be the Lyman Continuum. As you can see, MUSE, here's the wavelength range of MUSE where we can find Lyman alpha, and the Lyman Continuum can be found in the HDUV band 336 or also 275, but I'm focusing on the 336 band to detect the Lyman Continuum emission. I also make a redshift cut for my selection because As I already said, at higher redshift, the IgM is not very transparent for Lyman Continuum emission, so I'm focusing on the redshift 3 to 4 here. The first result is that I find 6 individual Lyman Continuum LyC candidates, which you can see here. So on top is the UV continuum band, which is the 814 band, and then here you have the Lyman Continuum 336 and also 275. There's already been a study by Rohai Naidu earlier who looked at a slightly lower redshift range, redshift of 2, and also found 6 Lyman Continuum LyC candidates. So while this is very exciting, if we want to understand the connection between Lyman Continuum and Lyman alpha, the sample is still not quite big enough. So now I'm also doing stacks of objects. We have lots of Lyman alpha emitters that we found in MUSE. But as I said, it's important to make a useful selection of objects in order to only use objects that can contribute signal to the stack. And this is what I'm doing with this plot here. So I'm showing the measured flux at 1500, so the UV continuum flux. And on the y-axis, the Lyman continuum limit over the UV continuum flux. So this means I assume that each of the objects is detected by one sigma signal, and this is the flux that would then contribute to the stack. And on the top here, you can see the axis for the blue line, which is significance. I'm adding up all objects starting from below, and you can see that the significance has actually a maximum. So if I stack more objects, the significance goes down again. So I'm only using the lower objects, which you can see here, up to the maximum, theoretical maximum of the significance in order to only use objects that contribute to the stack. So basically, the argument is if the object is already very faint in the UV continuum or even undetected, which we have lots of objects in MUSE, as I said, then it will also not be able to contribute to the Lyman continuum and only add noise. So I'm having 60 objects here for my sample to stack. And another thing that I have to keep in mind is, as I already mentioned, the IgM transmission. I am using 10,000 lines of sight from Inno et al. To do the IgM correction. And as you can see, while most lines have no transmission at all, there are some, especially at lower redshift, with still a high transmission in the IgM, which you can also see in this plot. Every of the gray dots is one of the 10,000 lines of sight, and even at redshifts above 3.5, there are some clearer lines of sight. So now to the stacking. As I said, I make a redshift cut. I also exclude objects with bright neighbors, and I mask the neighbors and hot pixels or cosmics, and use the selection that I just showed. And this is the result. You can see that in the 336 band, I actually do detect a signal with the selected objects that I have. The signal to noise is roughly 5 if I include the individual candidates, and 4 if I exclude the individual Lyman continuum candidates. And here you can see as a comparison the UV continuum. So now how do we get an escape fraction from those stacks? First of all, I want to highlight that with a certain signal to noise that I measure, there's a broad distribution of possible underlying escape fractions. So to estimate this, I make models of objects by using the UV continuum that I measure and an intrinsic UV continuum to Lyman continuum ratio, which I get from models from Starburst 99. One example can be seen here in this plot. And then I assume a specific escape fraction in certain steps, and add noise according to the 336 band, and also take the IgM into account. And then I do this 10,000 times with all the objects that I have, and always stack them and measure the signal to noise to see what the distribution would look like. And this you can see in this plot here. So here's the occurrence of escape fraction values over the escape fraction, and the different colors of the lines are the different signal to noise values that I measure in the stack. So what I want is to now be able to read from the signal to noise that I measure what the most likely underlying escape fraction for Lyman continuum would be. So you can see these two lines correspond to a singleton noise of 4 to 5. So the distribution is rather wide. So even with such a high singleton noise, there's a possibility that the escape fraction could be as low as 20%, but the most likely escape fraction would be around 80% for the selected objects. Now keep in mind that this is not the escape fraction for the whole sample of Lyman alpha emitters, but just for those that I selected, and also the escape fraction could still be lower than this. So now to the part that I mentioned before, I want to understand if the Lyman Continuum emission is connected to Lyman alpha emission. And for this, I separate my sample into two different halves, the half with a high property and the half with a low property of the line. So properties like equivalent width, full width half maximum, peak separation, and asymmetry. And what I find is that the stack with the half of the lower equivalent width has a slightly higher signal to noise, also with only single peaks, so very narrow peak separations, and with a rather large asymmetry, which means for lines that have a broader red wing. But you have to keep in mind that I'm taking the spectra from MUSE. So even if I say, okay, the stack with only single peaks has a higher signal to noise in the Lyman continuum, this could also mean that we just can't resolve the double peaks in the MUSE spectra, because if the separation is closer than 200 kilometers per second, it's not possible anymore to detect the double peaks. So this could be a reason for the signal here, which would fit well with the models. So this is my summary. As I said, I detected 6 individual Lyman Continuum Mika candidates. I am making a specific selection to only include objects in the stacks that would contribute to them. I find escape fraction compatible with 80%, and I find a higher signal to noise for the lower half of equivalent with higher asymmetry, and for single peaks. And with this, I thank you for listening, and yeah, we'll take questions.
Okay. Thank you very much, Josephine. Yeah, we'll start with very few questions. Aswin Vijen asks, have you tried alternative SBS models for the intrinsic spectrum BPAS? Do you think that would make a difference?
Yes, definitely. So I have started to look at BPAS models because I think that in Starburst 99, the Lyman continuum is predicted not to be that strong. So I find a very high escape fraction. I think if I'm using BPAS models, this escape fraction would not be predicted so high if I'm using a different intrinsic ratio between the UV continuum and the Lyman continuum. But this is something that I'm going to investigate now, yes.
Okay. Then Valentina asks, is it possible that some of your candidates are lower redshift interlopers?
Yes, so this is why I still call them candidates. There, for example, these two here, which are detected in the 275 band, which is quite unlikely. So we would expect from the IGM transmission that not much would get through here. We did some tests with different MUSE depths to see how often there are superpositions or wrong classifications, and the ratio for this is actually really, really low. So of the 6 individual candidates, statistically 2 could be superpositions or wrong classifications, but definitely not all of them.
Okay, then one final quick question. Why is the stacked Lyman continuum image peak offset from the center? How do you treat offsets of Lyman continuum from the optical profile centers?
Yeah, that is something that has been troubling me a lot. So I have done several tests to check why there is an offset. So I can exclude that it's something that there's something wrong with the positions that I'm using, because if I stack lower redshift objects, there's no offset. I also did bootstrapping, but to make sure that it's not just a single object, or yeah, but the bootstrapping showed that the offset is quite persistent. So I have no idea. It could be chance alignment, or it could be that there are some yeah, something in the data that produced that offset, but I have not yet found a reason for this, unfortunately.
Okay, well, thank you again for a very nice talk.